Assalamualaikum. My name is Muhammad HAKIMI bin Muhammad SUFIAN, S76681. Today I want to present about ODE. An ordinary differential equation (ODE) is an equation containing one or more derivatives of unknown function with respect to a single independent variable, such as time and position. The term ordinary distinguish ODE from partial differential equation (PDE), which involve partial derivative with respect to multiple variables. ODE are crucial for modeling how quantities change and evolve over time or space. Difference between first order and second order ODE. First order separable ODE, dy dx equal to fx gy. It can be solved by separating variable. Second is linear ODE, dy dx plus pxy equal to qx. The integrating factor method is used. Multiply both sides. Last is exact ODE, mxy dx plus nxy dx equal to 0. Second order ODE, homogeneous second order linear ODE, a kuasa 2 y per dx kuasa 2 plus b dy dx plus cy equal to 0. Second is non-homogeneous second order linear ODE, a d kuasa 2 y per dx kuasa 2 plus dy per dx plus cy equal to fx. The second order ODE have different general solution.
Hello everyone, my name is Nisha of PANNEERSELVAM and my metric number is S76679. Today I'm going to explain why ordinary differential or ODE are so important in engineering. This equation helps us describe how things change over time, like heat, vibration, current and even water levels. In electrical engineering, ODE describe how current and voltage behave in circuit. For example, in RL circuit, the current flow in first order differential equation. In mechanical system, ODE are more model vibration. The second order equation show how mass on spring with a damper move. It is very important in a designing system like vehicle, suspensions and earthquake resistant building. Moving to the next, in fluid mechanics we use ODE to predict how quick a tank will fill or drain. This first order equation is common in water treatment and chemical industry. Lastly, in thermal engineering, ODE describe how temperature change over time. Newton's law of cooling is a great example. It helps us design efficient heat exchange and insulation system. To summarize this, ODE are very everywhere in engineering and electrical to mechanical, fluid and heat. They help us to solve real world problem by predicting how systems are involved with time.
So I'm going to talk about the application of ODE in the engineering, that is in RC circuit, specialized in charging a capacitor in the power supply. The question is, write the differential equation describing the voltage across the capacitor V sub Ct, and then solve for V sub Ct and find the voltage across the capacitor at t equal to 1 second, and lastly determine how long it takes to reach 95% of the supply voltage. Terusnya, untuk solution kita apply formula yang diberikan. V0 sama dengan 12 volt, R resistor sama dengan 2 k ohm dan C kapasitor sama dengan 470 ounce Fahrenheit. Kita menggunakan Kirchhoff's law, that is V0 sama dengan RC d V sub C per dt tambah V sub C. General equation dia V sub Ct sama dengan V0 dalam kurungan 1 tolak E kuasa negatif T per RC. Time constant T sama dengan RC, iaitu 2000 darab 470 kali 10 negatif 6, dapatlah 0.94 second. So voltage over time dia adalah V sub Ct sama dengan 12 dalam kurungan 1 tolak eksponen negatif T per 0.94. Voltage at T sama dengan 1 second, jadi kita masukkan 1 dalam nilai T, iaitu V sub C 1 sama dengan 12 dalam kurungan 1 tolak eksponen negatif 1 per 0.94. Adalah 12 dalam kurungan 1 tolak eksponen kuasa negatif 1.064 sama dengan 12 dalam kurungan 1 tolak 0.345, dan jawapannya adalah 7.86 volt. Waktu dia capai 65% daripada 12 volt adalah P sub CT sama dengan 0.95 darab 12 sama dengan 11.4. Jadi 11.4 tu sama dengan 12 dalam kurungan 1 tolak eksponen kuasa negatif 3 per 0.94 adalah 0.05. Jadi negatif T per 0.94 sama dengan ln 0.05. T sama dengan negatif 0.94 darab ln 0.05 dapat 2.82 second. Jadi itulah jawapan dia.
Hello, my name is LOUISTON. My matrix number is S76654. So I'm going to pick up where ARIQ left. So our question today is about the application of ODE second order in spring mass damper system models, mechanical vibration in structures. So without further ado, let's begin. A mechanical system consists of a mass of m equals to 2 kilograms and a damping coefficient of C equals to 8 Newton seconds per meter, and a spring of with stiffness is K equals to 10 Newton meters. The motion of the system is governed by the second order of ODE. So here is our formula, the formula that we are going to use, which is m d the power of 2 x over dt the power of 2 plus c dx over dt plus kx equals to f in the column T. So the first question for this is derive the characteristics equation for the system. And the second question, determine whether the system is overdamped, critically damped, or underdamped. Justify your answer. And C, which is the third one, briefly explain what this damping behavior implies for the system's response to disturbance. So here's the solution. So first, we are going to apply the formula with the given um, data, and our formula is Newton's second law, and the data would be mass, which is m equals to 2 kilograms, damping coefficients, which is C equals to 8 Newton seconds per meter, spring stiffness K equals to 10 Newton meters. So the formula that we use is Newton's second law, which is m d the power of 2 x over dt the power of 2 plus c dx the power of dt plus kx equals to f in the column T. So the first thing we're going to do is sub in the given values. So m is 2 kilograms, which is the mass, and then d the power of 2x over dt the power of 2 plus c, which is 8 Newton seconds per meter, dx over dt plus 10x equals to 0. So what we're going to do is divide it by 2 to simplify the equations. So how do we do it? We divide it by 2 for each of the data given. So it will become like this, which is d the power of 2x over dt the power of 2 plus 4 dx over dt plus 5x equals to 0. Why 4 and 5 and 2 is gone? Because 2 cannot be divided by 2. And then if 8 divided by 2 is 4. And then 10 divided by 2 is simply 10. And then now the third one is we assume the equation is x in the column of t equals to e over rt. So why is this? We rewrite it into an equation that more simple and assume it using this formula, which is r to the power of 2 plus 4r plus 5 equals to 0. So the next one is to determine the damping. So it would be like this, which is d equals to b the power of 2 minus 4ac. So 4 the b equals to 4 to the power of 2 minus in the column 1 multiply by 5, and then it will be 16 minus 20, and then the result would be 4. And then we check it again using inequality, which is it's c the power of 2 equals to 8 the power of 2. So the answer would be 64. And then we rewrite using this formula, which is 4nk equals to 4 times 2 times 10, which equals to 80. So 80 would be our damping number. So next thing we do is compare. So since c the power of 2 equals to 64, it is lesser than 80, which determines the system is underdamped. Since the dam is underdamped, the system will oscillate with decreasing amplitude over time, not stop immediately but gradually settling down. That's all for me. Thank you.
Today, I'll be discussing how ordinary differential equation or ODEs play a crucial role in modeling and analyzing dynamic systems in engineering. So let's dive into two real-world examples to see how ODEs are applied. First, consider an RC circuit, a common component in electronics. So here, the relationship between the input voltage and the capacitor voltage is described by a first-order ODE. This equation helps engineers perform transient analysis to understand how the circuit responds over the time and design filters that shape signal frequencies. Without ODE, optimizing these systems would be far more challenging. So now, let's take a look at a mechanical system, the spring mass damper. This is a classic example where a second-order ODE models vibration and damping effects. Such models are vital in designing everything from vehicle suspension to earthquake-resistant buildings. By solving this ODE, engineers can predict system behavior and ensure stability under various conditions. So in summary, ODEs are so powerful for translating real-world dynamics into a solvable mathematical problems. Whether it is electronics or mechanical systems, they help us design, analyze, and innovate.
Why ODE useful? First, ODE help engineer predict system behavior. With the right equation, we can forecast how a system will respond under different conditions. Second, ODE improve system performance and help prevent failure. By understanding system dynamic, engineers can identify potential issues before they happen. Third, ODE bridge the gap between pure mathematics and practical engineering. They turn abstract concept into real-world application. And finally, ODE drive innovation in fields like electronic, mechanical system, and control system. They are essential tools in modern technology development. Process from equation to design. It starts with ODE equation, which mathematically describe the system, and then that leads to a system model which simulates how the system behave. Next, engineers then find an engineering solution based on that model, and finally all of this result in an improved system design that's more efficient and reliable.